Hello, welcome to my next video. This is Ramin, and in this video I want to introduce you a practical way to connecting SCADA devices such as PLC, inverter or HMI to the computer. In a regular SCADA system, for connecting these devices, you can easily build a block, for example in HMI, and send your command to the inverter or PLC only by using the address of PLC or inverter and their target registers. But sometimes circumstances may arise. You have to do this yourself by your own code in a regular platform. I have connected my laptop to the three-phase motor using inverter over a industrial Modbus controller. First of all, let me show you how the software works. Through the software, you can easily set the speed of motor, the acceleration time, deceleration time, and send a run command in any direction. During the running the motor, the numerical value of voltage, current, power, and RPM can easily be shown. And you can change the speed of motor, and smoothly these amounts are shown. Special thanks to Mr. Faramir Zlikshu, the company's chief engineer, for his guidance to smooth performance of the software. I've connected my laptop serial communication standard from RS-232 to RS-485 using MOXA converter, and connect my RS-485 output to the inverter. As you know, this cable can be up to 1.2 kilometer. Because the voltage level in RS-485 standard is differential and the environmental noises can't have effect on wires. About inverter, the input power supply is single phase, and the output which can be support my motor is three phase. The communication between inverter and laptop is doing by RS-485 using modular connector including to inverter controller. Firstly, you must change these three parameters in inverter. B17 for setting the inverter address, which is 1 in this project. A01 for setting speech source, which is 3 for using RS-485. And A02 for digital operator or coding state. Only pins 3 and 5 in RS-485 port in inverter are using in this project. We must send this frame to the inverter from computer, respectively the address of inverter, the type of command, which we use only 6 for commanding and 3 for monitoring, the address of register, and the numerical value of command. Finally, CRC high and CRC low bytes compose our frame. Let me look at the Modbus Industrial Protocol CRC generation. For correct sending a frame of command like this, and this frame are using for monitoring frequency from inverter, we should follow this rule to produce CRC bytes. This rule is the Modbus CRC method. For being ensured that all of these bytes will be received by inverter correctly, we should use an industrial protocol such as Profibus, Profinet, Canopen, or Modbus. In the first step, the first byte of the frame, 01, must be operated by exclusive OR with 16 bits of 1. The result of XOR should be shifted until the result to be 1. First shift and second shift. In the next stage, the polynomial value of Modbus Industrial Protocol A001 should be operated by XOR with the result. This operation will be continued 8 times. The result will be the first step of CRC. In the second stage, the second byte of frame, 03, starts its shifting journey by the first step CRC. First step of CRC and second frame. When all the 6 bytes are operated by this method, the result of last stage will be our CRC. Providing an example through some light to these explanations. For better grasp, I wrote a simple program for these operations. All of our operations are entered to this program, and the rule of CRC are producing by the software. In the frame of monitoring the frequency from inverter, CRC generation, the first step of CRC, second stage, and other, and or final CRC. For each byte of frame, we should write a simple for next loop like this. Each byte of frame and writing a simple for next loop to producing CRC.